But it's a real honor to be here. I appreciate being selected for this lectureship. It's an exciting chance to come to Utah also because it's a real epicenter, I think, historically, even currently, for work in this area of bio-integrated electronics. And we've been trying to make our own contributions to this field based on our research at Illinois over the last 5-6 years, and that's what I'll tell you about today. And I'll try to give you a sense of what we're trying to do that might be a little bit different and might be a contribution to the broader field. But before I do that, I'll try to just give you a motivation of what biointegrated electronics is as a technology, at least as we're thinking about it, and how it relates to maybe more conventional forms of electronics. And then really step you through the key ideas that have worked well for us in terms of material strategies, assembly techniques, mechanics design approaches, and then conclude with some system-level implementations of these ideas in devices that have clinically relevant modes of use in neurology, cardiology, and in physiological status monitoring brain-machine interfaces in the form of this kind of epidermal electronics, as we're referring to it. So if you're in electrical engineering and you think about electronics and the future of electronics, mostly you'll think about Moore's law scaling, which is an amazing trend that's characterized the development of silicon integrated circuits from the very early days, in which the number of transistors per die is doubling every 18 months. That's being driven primarily by a reduction in the critical dimensions of those devices. The overall processor chips are not changing in size very much. So devices are getting smaller and smaller, and that's been a tremendous way to drive the technology forward to the point that it's really a ubiquitous feature of our daily lives by now due to the kind of advanced functionality that's possible. And this is an important future in electronics. Make no mistake about it, this is going to continue. Many people are going to be able to make contributions to research topics that are going to be critical to enable this continued scaling. But if you think about the problem statement that's being addressed by this form of electronics, it's really that the transistors are never as fast as you want them to be. You never have enough of them, and they're never small enough. You haven't packed enough of them per unit area. And so you're always trying to increase or improve those metrics. And that's an important dominant form of electronics today, and it will be into the foreseeable future. But our thought, and I think a lot of the work going on here, is really along the lines that might not be the only future in electronics, that there may be other classes of electronics that seek to address other problems. And instead of transistors not being fast enough or not having enough of them or not being small enough, the problem statement in electronics that we're interested in, and others as well, is that all conventional electronics, high-performance forms of electronics, are built on monocrystalline semiconductor wafer substrates, which themselves are rigid, planar, and brittle, thereby imparting those geometrical and mechanical characteristics to the circuits themselves. And that those kind of properties are fine for lots of applications of electronics, but maybe not all of them. And maybe these characteristics restrict application possibilities. And so with that in mind, our solution to this problem has been to exploit high-quality monocrystalline semiconductor nanomaterials in strategic ways to build electronics that have the electrical properties of wafer-based conventional silicon integrated circuits or RF analog devices, but with the mechanical properties of a rubber band. And we're trying to do that because we think that if you can successfully realize a technology of that type, it could open up new classes of application that can complement those that are already well addressed by wafer-based forms of device technologies. And so you might imagine many different types of applications that would open up by removing those design constraints associated with the wafer format of conventional electronics. And there's probably lots of them. We've thought about a number of them over the years, funded for various types of systems. I think over time we've kind of gravitated to these two because we think that they're the most appealing for a lot of different reasons. And one is this area of bio-integrated electronics, wherein the electronics is designed to geometrically and mechanically match tissues of the human body, either the outside surface of the body in the form of the epidermis, so building electronics matched to the epidermis in a mechanical and geometrical sense to enable really an intimate and non-invasive coupling of electronic functionality with the body, with skin as the integration point, would represent one example of that kind of technology. Another one would be to use electronics interface to internal organs, tissues such as the brain, or the heart, where you could do important monitoring functions or advanced surgical procedures with the full power of silicon integrated electronics to improve the levels of functionality. So bio-integrated types of integration that are impossible to achieve with a wafer-based, more conventional format for the devices. So that's one area. The other area that I think opens up with this kind of stretchable electronics technology is in bio-inspired device design. And so there the notion is that nature and evolution have come up with lots of solutions to very difficult problems in technology, and none of those solutions look like a silicon wafer. And one example is the mammalian eye, which is a spectacular imaging device, partly because the detector has a hemispherical geometry, and that's a lot different than a planar CCD chip that you would find in a digital camera that you could buy today. And so we've been focused on ways to form arrays of silicon photodetectors on hemispherical shells so that they can mimic the geometry of the biological retina to build cameras that have extremely wide angle fields of view, low aberration, uniform illumination with very simple imaging optics up front to make a biologically inspired type of camera. So that's been a focus of a lot of our effort over the last few years as well. I won't say anything more about that in this talk, but really focus on these kinds of applications as targets for the technology we're trying to develop. Okay, so if you think about these kinds of devices, there would be a number of different conceptual strategies you could think about in achieving this kind of mechanics and form. And one would be bail out of silicon and go to some new classes of materials, carbon nanotubes, graphene, maybe polymer-based semiconductors, put those onto rubber substrates and begin to try to develop electronic device technology that way. And I think there's a lot of appeal and there's a lot of promise for those kinds of approaches. We've worked them over the years, continue to work them. But it's challenging because those are fundamentally new materials. You have to develop completely new process sequences, completely new device architectures, circuit designs, and so on. So the thought would be that if you want the fastest pathway to realistic devices of this form, maybe if you could figure out how to use silicon gallium arsenide in that kind of system, then that would be the most attractive way to build out a technology in the minimum possible time. And so if you think about silicon, it is conventionally found in a wafer-based format, which is inherently incompatible with what I'm trying to describe to you here. But if you create silicon in ultra-thin formats, in geometries such as nanoribbons or nanomembranes, then a couple of really useful things happen by virtue of pretty simple elementary aspects of bending mechanics. And the first one is that when you make silicon very thin, so conventional wafers may be 0.5 millimeter thick, let's say you make silicon 50 nanometers thick, so a factor of 10,000 smaller in thickness, what happens is it becomes mechanically floppy, almost like a noodle. So you take a silicon wafer like this, you can shave off the near surface region, monocrystalline sheets and ribbons of silicon in that 50 nanometer thickness range. And because the bending stiffness or the flexural rigidity depends not only on the intrinsic mechanical modulus of the silicon, the Young's modulus, but the cube of the thickness, what happens is you go from a bending stiffness that's maybe 10 Newton meters at the wafer scale down to a bending stiffness that's maybe 10 femtonewton meters at the nanomembrane scale. So you save, maybe 14, 15 orders of magnitude in bending stiffness. So a wafer is rigid and brittle. Thin sheet or membrane of silicon is floppy and flexible. And that's kind of the direction you want to go if you want to create these kind of mechanical properties in a circuit. That doesn't get you all the way there, but it's a step in the right direction. I'll come back to that in a second. So that's one consequence of making silicon very thin. The other one might not be quite as obvious, which is that in these thin formats, van der Waals forces and certain properties of energy release rates driven by changes in temperature in dissimilar materials lead to a materials format that's sort of sticky in sort of a qualitative sense. And this is just a demonstration of that characteristics. So this is a beam of silicon that we printed onto a substrate that's structured with a ridge here. There's no adhesive here. Just the contact right there is sufficient to keep this thing in a suspended format. So these materials can be delivered down to diverse substrates, and they can bond well, and bond in a lot more robust fashion than you would be able to achieve in wafer bonding, because, as an example, the energy release rate associated with opening the interface between a bonded sheet of silicon and an underlying substrate, driven by differences in thermal expansion coefficient, scales down linearly with the thickness. So as you get thinner and thinner, the energy release rate goes down, and so the propensity for fracture to form at that interface is decreased. Again, by many orders of magnitude, because you're starting at a wafer thickness and you're coming down to this nanomembrane thickness, so maybe 4 orders of magnitude reduction in energy release rate. So by making them thin, they're flexy and floppy, they're also sticky, so you can deliver these down onto a sheet of plastic or a piece of rubber, and they bond well. They don't tend to delaminate by virtue of this kind of mechanics. Okay, so that geometry for silicon is appealing. How do you create it in the first place? And one way to do that just relies on simple anisotropic etching tricks. So if you take a commodity silicon 111 wafer, which is already extremely highly developed piece of materials technology, it's really commodity in cost, and you do a two-step etching that involves first a trench etch to define sort of trenches properly oriented to the crystallographic directions in the underlying silicon substrate, and then you passivate the top surface and the sidewall, dunk this thing into an anisotropic chemical etchant, wet chemical etchant like KOH or TEMA. Those etchants will run along the surface of the wafer at about a factor of 500 times faster than it runs down into the depth of the wafer. And so in those that two-step etching process, you can slice off the near surface region of the wafer, then nanoscale ribbons or membranes of semiconductor-grade monocrystalline silicon. So the thickness here is about 150 nanometers. Here we etched along the interface there, terminated the etch right before it completely undercut, just to illustrate what's happening there. And as you can see, you fracture this thing off the side. These things are floppy and flexible. Note that these are designed to remain tethered to the underlying wafer at their endpoints, and that becomes an important feature of this route to semiconductor nanomaterials, and I'll come back to that in a second, which is to say that these anchor structures can be designed such that the ribbons don't simply float off into the etching bath even after they're completely undercut etched along their lengths. So that's one way to do it with silicon. You've only consumed the top surface of the wafer. You can do this over and over again, work all the way down through the thickness of the wafer. And so a single commodity chunk of material becomes a source of billions of these kind of nano ribbon building blocks that could be used for devices, as I'll show you a little bit later. So that's one way you can do it. If you want to do optoelectronics or RF analog electronics, you want to do LEDs, it would probably be useful to have similar conceptual routes to materials based on compound semiconductors. And there are ways to do that as well using top-down growth techniques in this case. This is an example in gallium arsenide. So you start with a wafer, you do MOCVD growth of multi-layer stack of active material, gallium arsenide, separated by epitaxial layers of high aluminum content, aluminum gallium arsenide. And that's interesting because if you etch down through that multi-layer stack and dip it into an etching bath of HF, you will eliminate the aluminum arsenide layers at a rate factor of 1,000,000 times faster than the gallium arsenide. So that multi-layer stack becomes a starting point for lifting off bulk quantities of gallium arsenide nanomembranes. And in that process, the gallium arsenide substrate is sort of catalytic, so you can actually use it again to regrow another multi-layer stack and do this over and over again to create large quantities of, again, high-quality epitaxial material that can be used as a building block for active devices. And this is a natural extension of single-layer epitaxial liftoff approaches that have been explored in the past, but this multi-layer configuration makes a much more efficient utilization of the growth chamber, thereby driving down the cost of this kind of material generated in that way. So if you lift it off, you can do it in extremely aggressive stacks. Here's an example of a 40-layer MOCVD stack of gallium arsenide films, 200 nanometers thick, separated by aluminum arsenide at 20 nanometers. This is good for, let's say, RF MESFETs. You can do more sophisticated things. There's a stack designed for a single junction solar cell, and you can use the sacrificial separation layers to separate it from a stack for near infrared photo detection. MESFET layers down here, you lift all of that stuff off. It's a scalable approach that can be used for many classes of devices. But at the end of the day, you end up with material that looks like this. So you lift it off of the wafer, goes into the solution etching bath. You can redeposit it down onto a piece of filter paper. And this is what it looks like. So this is the sort of bulk quantities of single junction gallium arsenide solar microcells generated in multi-layer growth stacks like those that I showed you before, about 200 microns on the size of platelets. And these materials are about 2 microns thick to optimize absorption cross-sections for solar radiation. So those are ideas in materials, but this is not obviously a solar module. And what I showed you before in silicon, that's not an integrated circuit. So what you need to do is add on top of that idea to nanomaterials an assembly technique that allows you to take these little bits and pieces, integrate them in deterministic configurations on a target substrate so that then you can come down with interconnect metallization and wire them up to make a functional system. And so how do you do that? One way to do it would be to make a solution slurry of this kind of material and then deposit it down onto a substrate that has pre-patterned areas of surface chemistry or relief, such that as these materials sediment down onto that substrate, they sort of, in a guided self-assembly approach, land in places where you really want them. And that's an interesting conceptual route. Achieving the kind of engineering yields that are useful for realistic systems is really challenging. And so I think it remains a topic, an interesting topic for research. We work on that problem. Others around the world do as well. But in parallel with that, we've tried to develop things that are more deterministic in the control of the assembly process. And for that purpose, we've sort of explored ideas that are based on printing with soft stamps. And the key concept is that because you're lithographically defining these materials, you know where they are, their spatial positions and their orientations when they're on the wafer. It's only when they wash off into the etching bath that you have to worry about this, full assembly from disorganized state to organized state. And so it comes back to that anchor idea that I mentioned before. Undercut these things, but use strategic points at their periphery to keep them tethered to the underlying wafer so that they're completely undercut but not washing off into the etching bath. Then come in with a soft elastomeric stamp with strategic features of relief on its surface, contact this stamp against this inking pad essentially, and if you do it right, van der Waals forces between the stamp and these platelets or membranes can be sufficiently strong that when you peel the stamp back, you fracture those anchor points, thereby lifting off these nanomembranes from the wafer source substrate to the surface of the stamp, thereby sort of inking up the stamp with silicon nanomembranes or gallium arsenide nanomembranes. And now you have the stamp inked, you can just index it over and print those nanomembranes down onto a target substrate like a sheet of plastic or piece of rubber. And you can do that in a step and repeat fashion, so you can take a dense collection of nanomembranes and then spread them out strategically only where you need them on the target substrate so they can be wired up together to provide the kind of function you're interested in building. So that's the idea. Now the details are important to make this thing work, and in particular you need to control the adhesion so that it's strong enough between the stamp and these silicon nanomembranes so that you can fracture those anchor points and in a high yield process ink up the stamp. But you don't want it too strong, because in the second step you got to get this material off of the stamp and then down onto the substrate. So in order to affect this kind of switching and adhesion, you could either exploit the viscoelastic properties of the silicone materials that we use for the stamp, and in particular, because of that viscoelasticity, upon fast peeling rates, the strength of adhesion between the silicon and the stamp can be high compared to the adhesion that occurs when you peel slowly. So you can kinetically control, peel fast on the inking, peel slowly on the printing, and that can affect that switching and adhesion that you need. The other thing that you can do is you can add relief features using biologically inspired adhesion principles from aphid insects, for example, to affect a pressure-induced switching in adhesion from strong to weak. And I'm not going to go into the details of those approaches. If you want to see more, you can look at those papers. But just make the point that those ideas can be made to work extremely well, especially when you implement them with a fully automated manufacturing system, a semiconductor nanomembrane printer, as it were. So here is one of the stamps. We have a vision system that allows you to look through that transparent stamp so you can index the relief features relative to the nanomembranes that you've created on the wafer host, and also then on the printing side allow you to register those semiconductor materials to pre-existing features on the target substrate. So there's donor wafer over here, stamp vision system. This is a Z stage. It goes up and down. We have load cells. We can control the contact pressure. And then a 2-axis stage on this substrate platform, which has the size of Gen 3 display glass. So back and forth, you can take material here, spread it out in a high throughput onto a target substrate. And because it's happening at room temperature, because of this interfacial adhesion physics, you can print onto almost any kind of surface you want. So here's an example of gallium arsenide nanomembranes, 250 microns on a side, 200 nanometers thick, printed out in a step and repeat fashion with that printer onto a sheet of plastic that we then subsequently wrapped around a cylindrical glass support, just to illustrate the flexibility that's afforded by the thin geometry. And in this case, it's about 1,600 of these gallium arsenide nanomembranes created in a dense array on a wafer host and then spread out in this sparse aerial configuration on the target substrate. And for this particular example, we had 100% yield. So these ideas in adhesion control and the manufacturing systems allow you to do this in a very systematic way. And so you can think about it as a parallel, massively parallel, high throughput version of pick and place technology. But it also has the advantage that allows you to handle materials that are far thinner and more mechanically fragile than would be compatible with a conventional pick and place tool. But conceptually, it's doing a similar type of operation, just allowing you to do that in a completely different way that opens up new engineering opportunities. Okay, so that's materials, that's assembly. Let me tell you a few things about devices then. So I'm not going to get into the details, but just make the argument that if you have a high quality semiconductor material like monocrystalline silicon, gallium arsenide, on plastic, you can go off and create very high quality devices out of that material. And you can do it in such a form that affords extreme levels of flexibility. Just by using that elementary mechanics principle that the bending stiffness is decreasing like the cube of the thickness. The other feature that's critical here is that the surface strains scale down linearly with thickness for a given bend radius. So if you make the silicon very, very thin, and in this case you use a very thin plastic substrate, you can make the entire integrated CMOS chip at a total thickness less than 2 microns. And in that geometry, you can wrap the circuit around even the sharp edge of a cover slip, which is a radius curvature of about 25 microns. So you use thin as bendable, surface strains decreasing linearly with thickness. And then one idea on top of that is required for this outcome, which is that you engineer the system so that the neutral mechanical plane is coincident with the most brittle material in the system, which is this silicon, in this case, the N and P type silicon. And the neutral mechanical plane just corresponds to the plane through the thickness of a sheet of bendable material where the bending induced strain is 0. That corresponds to the geometric midpoint in a uniform sheet of material. It's not quite at the midpoint in this case. We have several different materials, metal, oxide, silicon, and polyimide. But you can go off and calculate where it is and then choose the thickness of the polyimide so that neutral mechanical plane lies in the plane of the silicon, as illustrated here in the dashed red line. So if you do all those things, you have a very flexible form of silicon CMOS, but at the same time you have wafer scale mobilities and switching characteristics. So for this particular device, we see similar mobilities when we build a device on an SOI substrate, and that's a factor of 1,000 times better than what you can do with polymer or organic-based semiconductors, just as a benchmark or a point of comparison. And what that means is you get high current outputs, you also get high switching speeds, even with modest channel dimensions. In this case, it's a 2 micron channel, 3 micron source drain gate capacitive overlap. So, switching speeds in 350 megahertz range. So that's pretty good, but that's not good enough for biointegration because a sheet of plastic can wrap a sharp edge like that. A cylinder or a cone can't wrap a body part, can't even wrap a sphere. You need something that offers the elasticity that is inherent in biological tissues. So not only flexible, but stretchable, more like a rubber band or a piece of latex. So how do you do that? And it turns out another pretty simple idea allows you that kind of effective mechanics even with a brittle material like silicon. And the idea is you make silicon thin to make it bendable, and then you bond the silicon to a pre-strained piece of rubber. and the rubber is going to provide the elastic properties of the overall system. But when you bond the silicon to that pre-strained rubber and then you relax the pre-strain, compressive stresses on the silicon cause a spontaneous buckling instability that create a wavy shape in the silicon. So there's a silicon nanoribbon there, and it's sitting on a slab of silicone rubber after that pre-strain is relaxed. And so in this geometry, the silicon responds to tensile strains applied in this direction, much like an accordion would, which is to say that the amplitudes and the wavelengths of those wavy structures change as you stretch the system. So as you stretch it out, the amplitudes go down, the wavelengths go up to accommodate that strain without inducing fracture in the silicon. Likewise, you compress this thing, the amplitudes go up, the wavelengths go down. So you affect an overall end-to-end dimensional change, but the silicon material itself doesn't see very significant strains because the out-of-plane displacements are accommodating the in-plane strains. So it turns out the mechanics conceptually simple, but the details turn out to be extremely important from a design standpoint and not completely trivial. So we spent almost a year studying this and wrote a paper in PNAS back in 2007. But we sort of worked out the details now because in this kind of system, mechanics design becomes as important as circuit design. So you have to know exactly where the stresses and strains are to avoid fracture or avoid unwanted changes in the properties of the devices. Now this is a basic mechanics concept. That's not an integrated circuit, obviously, and if you have silicon on a rubber substrate, it's unlikely you're going to use that as a starting point for building MOSFETs because the rubber is way too dimensionally unstable to accommodate the kind of processing that you need to do to convert silicon into a transistor, diode, or something like that. But the same concept can be applied almost as a back-end packaging step on that ultra-thin neutral mechanical plane circuit. So you take the circuit, that thin circuit sheet, and at the very final step of the process, bond it to a biaxially pre-strained slab of rubber, allow that pre-strain to relax, and now instead of just this simple sinusoidal buckling geometry, you get something that's more complex and two-dimensional, but it still affects the kind of geometry that you want to afford this stretchability at the circuit level. So this is a chip scale implementation of that idea. So there's 10 ring oscillators here, CMOS transistors, N-channel, P-channel devices, and then inverters down here. And this is illuminated to sort of highlight the out-of-plane deformation associated with that wrinkling type of geometry. The strains that you compute in the active materials are fairly modest. But that wrinkling is good enough. You can stretch the circuit this way, or that way without inducing fracture in the system. So it becomes soft. It's also able to accommodate curvilinear shapes, both of which are key for biointegration. So this is an image that was collected by a group at our Beckman Institutes. We drop off a circuit. They came back with this, which I think is sort of aesthetically appealing, but it was also illustrating the physics. So they took a glass pipette, plunged it down into the center of this circuit, and you can see how sort of it can accommodate that kind of strain and induces this continuous curvilinear shape. You can also see that this particular line is in a state of tensile stress associated with that local force that's pulled out all of the wavy geometry. So if you were to continue to push down, that line would probably break because all of that wavy structure has been pulled out of it. So there's a finite range of stretchability associated with these ideas. It's about 20% or so, and so that can be useful. You can add elaborations on these ideas, as I'll show you in a second, to bypass that problem as well for applications that demand it. So you might think, you had a nice circuit, is nice and flat, now you kind of crumpled it up. And why would you want to do that? Well, you afford stretchability, but you don't adversely affect the properties because the strains in the active materials are far below 1%, sort of in the 0.1% range. So if you measure these devices, you see mobility values are comparable to the wafer scale analogs, both in NMOS and PMOS, and this ring oscillator works fine. So what's the problem? The problem is what I just mentioned. It's a finite range of stretchability, about 20%. That's not like a rubber band. It's close to tissue, but maybe you'd like something more in the range of 50% for biointegration. The other problem is that the devices themselves are not isolated from strain. So the strains they see are modest, but it's not zero. And because the mobility couples to the strain, as you stretch this thing back and forth, the output currents wiggle up and down by about 20%. That may or may not be a problem, depending on the circuit design and the kind of application you have in mind. But if you could solve those two problems, limited range of stretchability, and you could strain isolate the devices, that might be a useful thing to consider. And I won't go through all the details, but you basically take those same ideas and you elaborate upon them to improve the properties. In particular, you do two things. One is you can take that circuit and you can create the circuit in an open mesh geometry. So basically just etch away parts of the substrate where there are no active devices. So let's say there, and there in this particular case. Create an open mesh geometry. And then instead of bonding the entire system to the underlying rubber substrate, strategically control where that bonding is happening by lithographically patterning the surface chemistry on the silicone rubber substrate such that only the nodes in the mesh bond to the underlying substrate. So in this case, it's a rectangle or sort of a square mesh consisting of platelets of silicon nanomembranes interconnected by these non-coplanar arc-shaped ribbons. So the ribbons are not bonded to the underlying substrate, the nodes are, and this is what happens when you relax the pre-strain. So if you do this, you isolate the devices from strain and you enable a much wider range of stretchability, more comparable to rubber band, 150%, sort of that range. And so with this kind of geometry, you stretch it like a rubber band, but you can also conform it to highly curvilinear surfaces like the dimpled surface of that golf ball. So, you know, we have a way to integrate silicon electronics with a golf ball, and people tell me there are applications, in fact, that one might be interested in that emerge from that capability. But we're not pursuing that kind of thing. We're more interested in brains. And how can you bring electronics to the surface of the brain is an area where, you know, Utah folks have been real pioneers. We've been focused on ECOG systems, so non-penetrating ways to interface electronics to the brain and work in the clinical context of ways that people treat acute cases of epilepsy that are non-responsive to drugs. And that process involves, and we work closely with experts in epilepsy, clinicians who do this procedure routinely. It involves basically opening the skull cap to expose the brain, and then you laminate on the surface of the brain very coarse, kind of crude electrodes arrays that terminate in bulk wires, either in strip geometry or in a 2D geometry like that. So relatively small numbers of devices, electrode spacings on the order of a centimeter, something like that. And you rest that on the surface of the brain, and then you administer drugs that create or stimulate a seizure, induce a seizure, and you measure electrical recordings from each of these electrode pads, some of which might be in good contact with the tissue, some of which might not. If it's overlapped with a fissure in the brain, for example, you wouldn't get good signal there. But the surgeon then assesses the electrical activity of the brain to identify the region that's most closely responsible for the seizure. You peel this electrode array back, and then you just cut away that part of the brain. And that's the way the procedure works. So we thought that, you know, in discussions with clinicians, that if you could improve the resolution, spatial and temporal resolution of a monitoring system like that by a factor of 1,000 or 10,000, then that would be a great way to more precisely pinpoint the part of the brain that needs to be resected so you can minimize the amount of tissue that's removed. So we work closely with Brian Litt, Diego Contreras, a variety of people with the Penn Epilepsy Center at University of Pennsylvania's Medical School to develop a monitoring system based on the technology that I described to you previously for that kind of function. And this is actually a picture of a similar device for a cardiac application. I'll come back to that in a little bit, but it's basically the same as the one that we're doing epilepsy measurements with. It consists of about, in this case, 2016 silicon nanomembrane transistors in an array format in which we have 288 unit cells that consist of a thin metal pad that laminates onto the surface of the tissue. And then at each unit cell we have a multiplexing MOSFET here and then an integrated amplifier here to locally amplify the signal to improve the signal to noise. And the entire system is built on a floppy sheet that can laminate nicely against the tissue to provide, again, spatial and temporal resolutions far beyond what's possible with those more crude passive bulk electrodes I showed you a couple slides ago. So that's, I've said a lot about mechanics and assembly and materials. The other aspect of this is for clinical relevance, these devices have to operate when completely immersed in biofluids. And so that essentially means it's got to operate when immersed in salt water, warm salt water. And you might think, okay, that's not too challenging. I take my circuit and I embed it in a block of plastic. That would be a good moisture barrier, but that would destroy the mechanics. So the key thing is, how do you do encapsulation in a sufficiently thin film form that you still have the favorable bending mechanics, but you also have a good water barrier? And I can say that we figured out how to do that. It took about nine months. I don't have tremendous insights. It was basically an architectural change in the design of the circuit. The key thing here is you have to have exposed metal pads. So the places where those metal pads connect to the underlying circuits through vias become a channel through which water can flow. And if any water gets in, you immediately shock the animal, which is a bad thing to have happen. So you want to avoid that, and there are ways to use staggered offset vias and multi-layer geometries to avoid that kind of problem. So these devices operate underwater for several hours, just in the context of that surgical application. So here's an example of one of those devices. The corresponding paper is just in press now, laminated onto the surface of the brain of a cat. And in this case, it's an epileptic cat. They have a colony of such animals at Penn, and it's in a mechanical fixture that holds the animal still. So the device laminates on there, and then they can stimulate a seizure, an epileptic seizure in the cat, and then you can watch electrical activity monitored in real time with that kind of device. And so I'll show you a movie of what that looks like. This is more than the 288. This is a later device. I think it's maybe 1,000 pixels in this case on a pitch of about half a millimeter. And what I'll show is a spatiotemporal representation of the electrical activity measured across the area of that electronic sensor tape, where the local potential is rendered in a color format here. This is a single trace associated with the representative sensor node in that array that shows potential here on the y-axis as a function of time here. So this is 1 second, 2 second, 3 second. The drug, the neurotoxin, is applied at this particular point. The seizure doesn't start until here, until this time point. And so you'll be able to see this go. So there's nothing particularly notable. Oops. Hey, what's happening? Let's see if we can get this to go. Okay, here we go. So this is a red dashed line. There's the application of the drug. You begin to see some abnormal, unusual electrical activity, but still nothing in terms of the physical manifestation of the seizure. That doesn't happen until about a 1.5 second time delay. And what you'll see is that on a single channel basis, what happens right here is you begin to enter a very periodic oscillation in the electrical potential at that single channel. And then the corresponding spatiotemporal map shows a spiral wave instability that recurs with remarkable periodicity over and over again. And that's associated with the physical seizure itself. So I am told, my collaborators tell me, that this type of measurement has not been done on a live animal model before over this kind of area in an ECOG geometry. And this is critically enabled by the multiplexing electronics that's built into the sheet. So this could be useful for providing new insights into the neuroscience of epilepsy, but it also, maybe more importantly for us, has this clinical context, because skilled surgeons can identify from this kind of pattern of activity which regions of the brain need to be resected to eliminate the arrhythmia. The epilepsy. Arrhythmia is coming up. So that's kind of the functionality. The other things you can do with this are illustrated here. So there's another set of experiments. I won't go to the details. But because these devices are so flexible, you can wrap them around a soft insert, for example. And then you create a probe that can be plunged down into the sulci, into the hidden surfaces of the brain, or in this case, into the gap between the left and the right hemispheres, to provide high-resolution recording capabilities on those hidden surfaces at the same time. And so you can look at correlations in neural activity from one hemisphere to the next. So I think as a discovery tool for neuroscience, it looks like an interesting complement to other things that are already sort of out there. So I should just briefly mention that the same kind of device technology has relevance in similar kinds of surgical procedures that are used to treat cardiac arrhythmias. So the idea there is you map electrophysiological behavior on the surface of the beating heart identify aberrant regions, come back and resect or ablate. In this case, it's a little bit harder in some ways because the surface of the heart is so time dynamic. But because the devices are so thin, because of the adhesion mechanics that I mentioned before, these things can remain in contact without any penetrating pins or separate adhesives or straps with the moist surface of the tissue of the heart, almost like a piece of saran wrap, even as the heart is beating. So we actually have a ribbon cable out here to a PCB board. This goes to a computer, and I'll show you what this looks like. And this is a pig model, but the device is sort of laminated up over in this region, and then data is streaming out through that cable. In this case, we're not only measuring EP, but we're also stimulating the heart, pacing it in a spatiotemporal way. And so you can see the beat rate change dramatically right there because a graduate student hit a key on a keyboard over here, and then that changed the way the thing is pacing the heart. Okay, so let me take the last 10 minutes then to tell you about some work that we've been doing recently. I guess over the last 2 years, had a paper in August. And that is devices that laminate or integrate with the surface of the skin. Because I think although these internal tissues are interesting, that's really a clinical and a surgical context. And if you get devices that go on the skin, then maybe it could be more broadly useful technology for doing physiological status monitoring, for example, maybe prosthetic control. And if you think about the skin as a point of integration, the entrenched technologies sort of look like this, and you've probably seen these at the hospital. It's great for clinical settings, maybe research purposes, but these devices don't allow a very large number of electrode contacts to the skin just due to practical difficulties in managing these wires. The other thing is they're bulky and uncomfortable. Nobody wants to wear these things. They basically tape onto the surface of the skin. And they involve a design strategy where the electrodes are here and then the electronics is someplace else. So you also have to carry around a separate box of electronics to do anything useful. But this can be used to measure EKG or EEG, EMG, for example. Slightly more advanced embodiments involve taking the chips out of the box, putting them on a tape, and then taping that to the surface of the skin, which is also a solution that has some shortcomings. So what we had in mind is to try to build a class of electronics that looks like a kid's temporary transfer tattoo in terms of its mechanics, geometry, and mass density. And the idea is if you could make silicon electronics look like this, it'd be a great way to integrate with the skin, because these tattoos, as you know, if you've ever worn these things, are sort of mechanically invisible. They're not irritating at all. They don't constrain the natural motions of the skin. And because of the mechanics that I'll show you in a second, they adhere pretty well without much difficulty. And so the idea is to create electronics in this format, and more specifically create it in an ultra-thin geometry, maybe 5 microns, ultra-low areal mass densities to minimize mass loading on the skin, modulus matched to the epidermis, so maybe between 5 and 100 kilopascals, but also keeping it waterproof and air and water permeable. So this took a while to figure out, but we were interested in pursuing it for the following reason. If you think about conventional devices, a big problem is getting good adhesion over time. And you could view that as a material science problem associated with skin adhesives, or you could view it as a mechanics problem that emerges from the geometry and the mechanics of the device you're trying to adhere to the skin. And if you think about it in the latter way, you can go off and do mechanics modeling of electronics, say generic electronics as a modulus E and thickness H, mounted onto the skin, and think about what are the shear stresses that appear at that interfaces and the peeling stresses that appear at that interface that tend to drive delamination. And first of all, you can compute those as a function of normalized distance from the edge. So the edge is here in these two plots. And the first thing you see is the shear stresses and the peeling stresses are highest at the edge of the electronics. So the delamination starts at the edge, which is not too surprising. But it gets interesting when you compare the shear stresses that develop at that interface when the skin is stretched in a tensile mode. For the cases of silicon chip, a flexible circuit, so plastic, modulus of 5 gigapascal, thickness of 50 microns, and skin-like, so epidermal, so very low modulus and very small thickness. And you compute these stresses for these three cases and see how their magnitudes vary. So one thing you can look at is, say, the stress ratios associated with the silicon chip compared to the plastic sheet. And you find that in tension or in bending, the interfacial stresses are reduced in going from the chip to the plastic sheet by about a factor of 5. And so that factor of 5 means that you reduce the requirements on the adhesive between the electronics and the skin, but not by that much. It's not even an order of magnitude. It's only a factor of 5. So working on a plastic skin-integrated electronics is probably not that interesting. You're not doing that much better than just silicon chip. On the other hand, if you compare silicon chip to electronic skin, so epidermal format, that is these mechanical properties in that thickness, you find that those stress ratios, both for tension and bending, are decreased by 5 orders of magnitude. And so what that means is if you can create this kind of skin, electronic temporary tattoo, you might automatically solve the an interfacial adhesion problem by managing the stresses and reducing them without worrying about new adhesive for the skin. And so that's kind of what we've done, and that was the main motivation for trying to make electronics in this format. And you can see some experimental data and theoretical modeling that sort of confirms what I just told you. So you can look at silicone as a model for the skin, and then thin PDMS on top of it. If you stretch the silicon, substrate peeling starts at the edges. In this particular geometry, if you squeeze it, you get a buckling mode deformation that drives delamination at the center. But what you can compare is the tensile strain needed to initiate delamination as a function of the thickness of the electronics modeled by the PDMS here and its modulus. So 50:1 is lower modulus than 30:1. And so you can see it monotonically increases the amount of tensile strain that you can accommodate as you decrease the PDMS thickness and as you decrease its modulus. Same thing happens in compression. So thinner is better, lower in modulus is better, without bound, in fact. So the thinner you can go and the lower in the modulus you can go, the better. And you can see that in a simple experiment with 2 different formulations of PDMS with 2 different thicknesses laminated onto the skin. So here's about a millimeter thick standard formulation of a Dow Corning material, and you can see that this thing delaminates as you move the skin. You can see it there. In tension, you'll see the delamination start at the edge. There it goes. So you need to work on a new adhesive if that's the format for the electronics. But then, as I mentioned before, the other solution to this problem is to change the thickness and the modulus of the material and don't do anything with the adhesive. So this is just van der Waals adhesion. It's about a factor of 10 thinner and about a factor of 2 lower in modulus than what I just showed you. Same material, same interface chemistry, but now it doesn't delaminate just because you're minimizing those interface stresses that would ordinarily lead to crack formation, both in tension and in compression. So how do you do that in a circuit? So you have this low modulus rubber substrate matched to the epidermis. How do you load a circuit on top of that without altering the mechanics? And you really have to pull out all the stops in terms of the mechanics ideas that I discussed before and add an additional idea on top of it. So you make the circuit ultra thin, neutral mechanical plane, silicon nanomembranes, buckling in the plane, and then on top of that you create the circuit in an open filamentary serpentine mesh design like that. And if you do all of those things, then what you find is you measure the stress strain curves of a circuit configured in that way. You can generate a system, a silicon integrated circuit with modulus matched to the skin, about 160 gigapascals. This is pig skin in this case, consistent with finite element modeling of the mechanics. We know exactly what the stresses and strains are in this thing. And it has linear response to strain up to about 30%. Tissue, the skin starts to tear around 30%. So that's all the strain range you really need. So filamentary circuits and devices, in fact. So you create your MOSFETs in this kind of format. There's source, drain, gate. That's a silicon serpentine resistor for a sensor node for measuring electrophysiology through the skin. You still get wafer scale performance. It's just in this really funny geometry. You make strain gauges. There's solar cell and that same type of layout for the purpose of the mechanics. So this is kind of what it looks like after laminated onto the surface of the skin. This is a glass pipette, sort of puncturing the skin, not pushing too hard actually. It looks like that might be painful. It's not that extreme. It's a postdoc anyway, he can take it. So here's the open mesh geometry. Now once you have this skin-like format, it is tissue-like in every sense of the word. So you peel this thing back, it looks like a piece of skin you might pull off after you get sunburned. This is about that thickness and about that module. So it flops down on top of itself. So there's a practical matter of how do you even handle this stuff at this thickness and this modules. You can't pick it up and do anything with it. And so the way that we solved that problem is we just borrowed ideas from temporary transfer tattoos in the sense that we use a water-soluble polymer sheet as a temporary backing. You have the epidermal electronics on top of that. You laminate that against the skin, and then you wash away the polymer backing. So I have a short video that shows that mounting process. So as a postdoc, there's the sheet. So this is the plastic sheet. There's the circuit. So this is a demonstration platform, all kind of different device types in that filamentary mesh design, epidermal mechanics. And so the student is now washing away the water-soluble PVAs, polyvinyl alcohol, backing with water. So as that backing disappears, it will leave just the epidermal electronics adhered to the skin just by van der Waals interactions. No adhesives or penetrating pins, straps obviously. But it will hold it there. There's sufficiently strong adhesion that you can pinch and squeeze and stretch the skin without causing it to delaminate. And I'll show that kind of motion in a second. And furthermore, it doesn't change any of the natural mechanics of the skin because the mechanics loading and the mass loading effects are negligible. So there's the device after that polymer backing layer is gone. You can see the outer edge of that thin modified silicone substrate right here. And the circuit is right here, or this demonstration platform. So, as was mentioned before, there's an inductive coil here, an RF antenna there. There's an array of silicon MOSFETs there, RF diodes, LC oscillators over here, temperature gauges, strain gauges over here, and there's an LED right there in the center of that inductive coil. But as you can see, the skin deforms in the region of the circuit exactly the same way that it does away from the circuit. And that's just providing evidence that we've gotten the mechanics right. And it's matched to the tissue in this case. And we'll just show you what that looks like when you peel it off. Again, the absolute adhesion strength is not high, but the interface stresses associated with deformation are so low that it doesn't matter. So here it is. It peels off fairly easily, and you'll be able to see what this looks like then. Devices there, and there it goes. It's sort of ripped right there, and then it peels off. And you can see it there. There's something sort of disgusting about the whole thing, but anyway. And just for fun, we showed that we could use an actual temporary transfer tattoo as the substrate. So this is a device there. This is just commercial transfer tattoo, but it's a custom design. You might not know the history, but University of Illinois is no longer allowed to have an Indian chief as the mascot, so our proposal is to go to pirate. And so we have pirate, and there's U of I logo right there. So this is a custom tattoo designed by one of the postdocs working on this project. Minimum order was 1,000 of these things for $100. So if you want any tattoos, I can give you some. Not with a circuit. These circuits are all handmade, so we can't give those away. But this is what it looks like. So the circuit is right there. So the point is you can build off of this low-cost materials platform. There are adhesives built in here, so this is probably a more robust way to do the integration compared to what I showed you before. But as with before, the device itself doesn't alter the mechanics of the skin. And if you're into spy games and stuff like that, it's a good way to conceal the electronics. You can't see through the tattoos. So student was just highlighting where the mechanics, where the circuits are across that tattoo, and you'll see this little bit of deformation here. Again, the key thing to look for here is that the way that the skin wrinkles and deforms in the region of the circuit, it's exactly the same as the way that it deforms away from the circuit in the region of the tattoo. So the circuit is really mechanically invisible to all this sort of thing. And just to prove that there was electronics underneath there, the student will rub this part of the tattoo away with his finger, and then you'll be able to reveal the circuit behind there. You'll see this in a second. So there it is. You can kind of see the flake. I mean, that's a destructive process, obviously, but you can see the devices. So it's a good mechanical interface. It's also intimate in an atomic level sense, at least to our ability to measure it. And so it provides a good electrical interface. This is confocal micrograph of a serpentine intersection point on pig skin, and you can see the device is really conforming to the geometry of the skin. So what that means is you can do electrical measurements of ECG and EMG and even EEG. So if you're mounted on the chest, you can measure heartbeat signals, QRS waveforms. You're mounted on the leg, you can measure properties of gait. The signal quality is very similar to those paste-on electrodes, which use conductive gels that dry out over time. So the signal noise is quite acceptable. You can even do EEG. That turns out to be a little bit harder. The signal levels are much lower, but you can see characteristic patterns of alpha rhythms. We've done Stroop tests and other things just by putting these things on the forehead. So what do you do with this? I mean, one thing would be do continuous real-time monitoring of health and wellness. The other thing is a brain-machine interface. Could be interesting. And so as a demonstration of that, we took one of these devices, laminated on the throat, and then you can measure EMG as the person wearing the device is mouthing different words subvocally. And you can measure spectrograms of EMG signals recorded in that way. And we worked with a professor in electrical engineering, Todd Coleman, who developed pattern recognition algorithms who could take that data and bin the data in terms of a limited vocabulary of words. And then you can use that output to, let's say, control a prosthetic, or somebody has a problem with their larynx. They could use such a device to speak, or you could use subvocal communications, for example. My students were mostly interested in playing video games, so we made a simple interface to this game, Sokoban. So it's a simple thing. I mean, you have a cursor, you can move it up, down, right, or left, and use your neck muscles to control the game, just as a demo. So let me end with this, which is some very recent work we've been doing with folks at Johns Hopkins. So these devices can measure electrical activity. They can also stimulate, which is not too surprising. But if you combine those two things with the epidermal format, there may be opportunities in physical rehabilitation. So this is the first experiment of an epidermal electronics sheet that's doing sensing and stimulation on the hindquarters of an anesthetized rat. And so I'll play this movie. This thing is pacing and stimulating in a non-trivial way, and also at the same time measuring the electrical response of the muscle contractions to allow closed-loop feedback control over what's going on. And it's all in a format that doesn't constrain or restrict the natural motions of the skin or the underlying muscle. So this, still haven't quite gotten used to this video. There's something really strange about it. But anyway, you can see this, the paw rotates and then deflects due to the way that we're stimulating these electrodes. And you can see how this thing moves around as the muscle contracts. So rehabilitation might be an interesting area to explore for this kind of technology. So that's all I had to say. I would just highlight the senior collaborators have been involved in this work. It's very multidisciplinary. Yanggang Wang does all the mechanics modeling. He's a theorist at Northwestern. Placid Frere on the manufacturing systems. I showed that printer. Shuling Li on the multi-layer gallium arsenide epi growth. Todd Coleman I just mentioned on signal processing. And then for all of our biointegrated devices, we try to work with practicing clinicians, more so than researchers, so that we can develop something that has real-world applicability. So in neurology, it's Brian Lidd. Cardiology, these guys, rehabilitation I mentioned before. Igor Efimov also on cardiology. And so this is an example of our clinical collaborator, Marv Schleppian. So he does about 200 of these cardiac arrhythmia experiments and can kind of help us understand what's the most important type of functionality to bring to bear. He's at the Sarver Heart Center, and we have a startup company that's trying to commercialize some of this stuff. But the key thing is really good students. I mean, I think graduate students and postdocs that I've had over the years are really exceptional, and I want to thank them because they do all the work. And thank you for your attention. I'd be happy to answer questions if you have any.
Okay, we have time for a few questions. I would say that maybe one or two because there's a class waiting in the wings here. So please, some good questions.
Is there much individual variation in epidermal and mechanical properties? Do you think
Yeah, there's a lot of variation. In fact, if you look at the skin under your eyelid, for example, it's an order of magnitude thinner than the skin on your back. So it really varies not only from individual to individual, but even for a given person across the body, the thickness and the mechanics are different. So we have enough modeling know-how and materials versatility that we probably match almost any part of the body. But one point that I was trying to make is that matching is one thing. And so intuitively you think, okay, your mechanics match, that's what you want. But it's actually, you want the lowest modulus and the thinnest geometry possible. That's always better. So I think independent of variations, you always want as thin and as low modulus as you can go. So you don't really have to tailor it to a specific person or to a specific part of the body. Yeah. Well, we've done things that don't involve long residence times. And so I think there's a whole host of issues at materials level biocompatibility. And I know a lot of the guys here on the Utah arrays have thought very deeply about that. I mean, I think there's agreement in the community. There's the materials aspect to compatibility, but it's also mechanics and geometry aspect. We kind of focus on those second two things. I think there's a lot to be done. In terms of the technology, I think power supply and I/O are always the big issues. And so for a skin patch, you'd like to have a wireless link and maybe some storage capacity. Right now we're just doing inductive powering, and right now we just have hard wires coming out. We think I have the building blocks for a wireless radio, but we haven't done that. So there's a lot of things to do on the technology, also some on the materials. I think there's a lot to be done.
Last question will come from our professor.
Very nice talk. So your transistors were quite big.
Yeah.
In case you have like 500 microns.
Yeah.
So by
Yeah.
reducing them
Yeah. Yeah, that's a very good point. I mean, one of the things we like about some of these design approaches is they're fully synergistic with conventional Moore's law scaling, where the thickness of the silicon's going down, the device geometries are going smaller for a whole host of different reasons, but those geometries and thickness is perfect for this. So yeah, I think it's a great point. What we're able to do in an academic clean room is only scratching the surface of what would be possible for Intel, 22 nanometer node CMOS technology, which you could lift from a wafer and integrate in these formats. So these are very primitive. They're very coarse, but just constrained by what we can do in an academic environment. Yeah.
All right. Let's thank Professor Judd.